All right, getting into some Chapter 3 probability here. So this is worksheet A. Starting off with number 2. So we got two six-sided dice. Given a toss, so X is in the event that the sum of the scores is 8. So it's always important to kind of recognize what we're talking about with these two dice. It could be individual numbers, it could be a sum. So in this case, we're talking about a sum. We're looking at the sum of the scores is 8. Y is the event that their difference is 2. So find the probability of X and Y. So if we kind of put the words into place of the symbols, that means we're looking for scores where the sum is 8 and they have a difference of 2. So we're looking for any case where both of those statements are true. So we always want to throw in the word and for that little guy right there. Best tool for these is the lattice diagram. So the lattice diagram is the one where you would draw like a 6x6 grid, since we're talking about two six-sided dice, and then you just kind of identify the ones that would apply. Let me show you one that's kind of already been done for us here. So here's the one for this. So this is think of this as one of the die, and this would be the other die. So if we're looking for any cases where they have a sum of 8 and cases where they have a difference of 2, so on this one right here, if we were to find our sums of 8, so you got the 2, 6 right there. You got the 3, 5 right there. We got the 4, 4. You got the 5, 3. And you got the 6, 2. So you got 5 cases right there where the sums are 8. But this one specifically said they have a sum of 8 and a difference of 2. So I can only use the ones that have a difference of 2. So that would be our 5, 3 combos. So it could be a 5, 3, could be a 3, 5. So you have 2 cases where both of those statements are true. So it's a 6x6 grid, so there's 36 total possible. So 2 of those 36 fit that condition. So we would just say 2 out of 36. Reduce if you can, so 1 out of 18. Anytime you're answering these on a test question, as always, the rules apply either exact or 3 sig figs unless the directions say otherwise. If it's a fraction, you should always reduce. So this one here, we're just the same thing, but now it's the word or. So these are now cases where it can have a sum of 8 or a difference of 2. In an or statement, we count everything that's true about either one. So I get to count all of the sums of 8. I get to count all the cases where the differences are 2. And really just an easy way of doing that, again, would be with the lattice diagram. So you could use a formula. We do have a formula for this guy. It's the one that looks like A or B equals the probability of A plus the probability of B minus the probability of A and B. So we could use a formula for this, or you could just find the numbers on the lattice diagram and go straight off of that. Let me really quickly just show you with the formula. Because if you were going to use the lattice diagram for this, you would just find all those cases and circle them, just like I did with this one. So if you found all of the sums of 8, you could circle those. You would then also look for any numbers that have a difference of 2. Keep in mind you wouldn't count the same guy twice. So if you've already circled this as a sum of 8, you would not also count it as a difference of 2. Otherwise, you'd be counting the same guy twice. So just within the diagram, you just find all the cases where they have a difference of 2, add up all the ones that you've circled, and that would be your solution. So that's one way of doing it. The formula would look something like this, though. So if we're going to say probability of sum of 8 or a difference of 2, so probability for the sums of 8. So we're going to say probability that have a sum of 8 or probability that have a difference of 2 minus any overlap. So we don't want to count the same number twice. Oops. So that's what our formula looks like. In our formula packet, it's got A's and B's instead of X's and Y's, but it's the same formula. So this helps ensure that we don't count the same results twice. So like those 3, 5 combos. We got to remember to take those out, otherwise we'd be counting the same ones twice. So for this one right here, we'd say what are the sums of 8? We knew that there were 5 out of the 36 that had a sum of 8. Cases that have a difference of 2. if you were looking at that last lattice diagram, you would see that 8 out of the 36 cases have a difference of 2. But within those two selections, there were 2 items out of the 36 that we highlighted twice. Those were the 2 cases that had a sum of 8 and a difference of 2. So we got to subtract that 2 out of 36 so that we're not counting the same guys twice. And this is where we would get our result from. So now that adds up to 11 out of 36. All right, moving on, number 3. So A and B are independent events. So probability of A and B are given. So what's the probability of A or B? So really important use of formulas with these guys. So let's peek at those real quick. So for the A or B, again, using the same formula that we just used that looked like this. So you got A or B, you got A plus B minus A and B. So one thing that you got to notice on this is there is a formula within the formula. How do we get this item within the information that we were just given? So if you look right down here, if I have independent events, that means I can find A and B by just multiplying A times B. One thing that you really have to be careful of, though, is don't do this unless they specifically say that the events are independent. If they don't say that, you can't do this. So oftentimes students will do this on every problem, even though they weren't told that the events were independent. So don't ever use this formula unless you see this word given to you. So we're going to use that little formula in order to get this piece of our answer. And so we're just going to start plugging in some numbers for those. So going off of this, so we have the probability of A plus the probability of B minus A and B, and again I can say that A and B is 1/3 times 1/6 simply because they specifically told me that the events were independent. If I don't see that word, then I would not take this step. There would be something else going on there. So careful on your use for that. So anyway, so now that we have that, the rest is just kind of some simple math. So if we were to create some common denominators here, it looks like I'm going to get 1/18 out of this part. So let's see if we can put everything out of 18 real quick and do that. Your calculator can deal with the fractions. So if you didn't want to deal with the common denominators, you could certainly just use a calculator. But 1/3 would be the same as 6 out of 18. And 1/6 would be the same as 3 out of 18. So now if we add those up, 9 minus 1 gives us 8 out of 18, and of course we would reduce that. The probability of not A or not B. This is where the use of Venn diagrams really helps. So if you didn't watch my video on Venn diagrams, I really encourage you to do that, because there's some helpful places like this where Venn diagrams really can lead you to the right answer when other things aren't really there to help. So let me just draw this one out real quick. So if I were to have, this is going to be A, this is going to be B. Anytime you're doing a Venn diagram, you always start with the inside and work your way out. So this is the area of A and B, which we just figured out right here was 1/18. Since the probability of A is 6/18, if this is my circle for A, the best way to identify this area is to take all of A and subtract out what we already have in the circle, which is the 1/18. So I got to do 6/18 minus 1/18 to get the rest of this. So keep in mind now, if you do look at all of circle A, it does add up to 6/18, which we know is event A. So I know that's right. Part B, the total on that needs to be 3/18. So if the total circle is 3/18. If I subtract out what I already have, then this leaves me with 2/18. And so that's that area right there. What does that leave me with for the outside? Well, keep in mind, within this universal set, so we'll call this our universal set, this has to add up to 100% because we're dealing with probabilities. So if you look at what we already have, if I add those up, adds up to 8/18, right, which we already know from this. So this is 8/18, which means the other 10/18 must be out here, because I need a total of 1 if I were to add up every section within the universal set. But now look, if we consider this idea, where are the areas that are not in A or not in B? So if we were to shade that, remember in an OR case, you shade everything that's true about him, you shade everything that's true about him. So if I were to shade everything that is not A, that would be all of this space here. So that's everything that's not A. If I were to shade everything that's not B, so everything outside of circle B, that would be those areas. So when they say not A or not B, just look at all the areas that we shaded. We shaded everything except this guy right here. He's the only thing that didn't get shaded. So if I add up all the areas that did get shaded, they would add up to 17 out of 18, which would be our answer. So consider use of Venn diagrams a pretty helpful tool with some of those cases. In a case like this, it doesn't directly fit a formula that we have. So you would have to sort of tweak some of the formulas in order to make it fit. So sometimes if it doesn't directly fit a formula that we have, Venn diagram I think is the next best way to go. So moving on to number 4. So again, we're given some independent events, so really key word right there. And it gives us this information. So they just want the probability of A. So pretty simple, we just plug into the same formula that we've been using so far. So we know the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which I am allowed to multiply in this case because I was told that they were independent events. If they didn't give me that word, I would not have taken that step right there. There would have been something else I could have done. But anyway, if we just want to solve for A in this case, let's clean up a little of what we can. So I'm going to subtract that 0.2 over. Clean up the notation on the right side. So I'm just going to call that A, and I'm going to call that 0.2A for that group on the right side. Cleaning that up, it's 1A minus 0.2A, which is 0.8A. And now if I just divide that 0.8 over to the left, we have our solution for the probability of case A. So moving down to number 5, so for these events, again, we're given kind of some more information. So it says find the probability of A. Notice in this case, they did not tell us that we have independent events, which is why they just flat out told us what A and B are. We wouldn't have had another way to figure this number out because we're not told that they're independent, so you can't just multiply A times B. So in this case, they had to just give it to us for that one. So looking at our setup to find the probability of A, it's just the same formula that we just used. So we know the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which again, they had to give us because they didn't tell us anything about independent events, so we would have had no other way to come up with that number. So now you can just isolate A and get that by itself. So you could combine like terms on this side, so subtract looks like 0.16, and then you can subtract the 0.16 over to the left and get 0.44. And then now the probability of A given B. I know in our formula packet it's written a little differently, but the way that I taught it in the lesson and the way I would encourage you to learn it is to say the probability of A given B is equal to the probability of A and B over the probability of B. So your given always goes on bottom, the and statement always goes on top. I've always seen this as the best way to kind of understand the layout of that formula, but now I can simply plug in the numbers. They told me that A and B was 0.24, and they told us that the probability of B is 0.4. So that's it. That's your setup right there. You could just divide, or you could keep it as a fraction and reduce. I wouldn't leave it in decimal form in a fraction. You've got to clean that up to kind of simplest terms without decimals if you're going to leave it as a fraction. So moving on to number 6. Again, we got two more events, A and B. So if they are mutually exclusive, find not A or not B. So in this case, keep in mind that mutually exclusive means they have nothing in common. So your setup for your Venn diagram would actually look like this. There's no overlap. They tell us in the formula packet that anytime you have mutually exclusive events, A and B equals 0. So there is no overlap. They have nothing in common. So this is A and B. They're completely separate because they're mutually exclusive. So now if I were to do the same approach that I took with the Venn diagram before, and start out by shading the areas that are not in A, so there's everything that's not A. Also, if I shade everything that's not in B, so here's everything that's not in B, notice what we have. In this case, I shaded everything. So because they're mutually exclusive and had no overlap, to shade the things that are not in A or not in B is everything. So that would give you 100% probability, or 1. So moving on to B, so what if they are independent events? So now, as always, that changes things. So independent events means they can have something in common, and we find it by just doing A times B. So now looking at these guys, you got A or B, which is what we've done already before. So finding the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which we can now find by multiplying because of that word right there. So I can now find A and B by doing 0.6 times 0.3, for getting that guy right there. So just add those up. You got your 0.9, subtract that out, and you would have your answer. Remember what we do for the given, the way I just showed it in this problem right here. For A given B, the setup for that, the best way to set those up is to put A and B on top, which we just identified right here, over B. You always put the given on bottom, so whatever comes second goes on bottom. In this case, B was 0.3, so I can put that on bottom, and then just do a little cleanup. So if it helps, you can think of that as 0.30. So ditch the decimals, and if you reduce it, keep it as a fraction if you want. If you wanted to go pure decimals, just divide that out in the calculator. Number 7, so now you have two 8-sided dice, numbered 1 through 8. So when the two are thrown, T is the total score combined. Again, that's a sum question. So what's the probability that their sum is greater than 5? Really, the best way to do this, I still think, is with a Venn diagram. So, a lattice diagram. So if you were to draw out an 8x8 grid to represent the two dice that were tossed. So here's what it looks like on the worked out solutions. So this would be the first die that's tossed. This would be the second die that was tossed. And so for this question right here, looking for all the cases where the sum is greater than 5. So if we were to just highlight all those cases where the sums are greater than 5, so that's going to start you off with this row. So like 5, 1, 4, 2. So right here you got the sums that are 6, the sums that are 7, and so those just kind of keep going up if you kind of highlight all this area right here. So everything from the circled row and greater would fit all of those cases. So there's kind of two approaches here. I could just add up all the cases that I want, which would be all these dots, or if you look to everything below the circles, those are all the things that I don't want, which I could just add those up and subtract them from 64. This is an 8x8 grid, so I know there are 64 cases. So it might just be easier, since this is a smaller bunch, to just say, well, let's just add those up and subtract them out of 64 and see what's left over. That must be all the cases here that we do want. And so if you looked at these cases, you have 10 dots below the circles. So if we did 64 minus 10, that must mean that there are 54 cases that I want to keep. And so this is where we could get the 54 out of 64 for part A. So jumping down to part B, so what if they were tossed twice? What is the probability that the sum is greater than 5 exactly one time? That simply means it's going to happen on one of the tosses, and it will not happen on the other toss. And so you kind of have to consider sort of both cases on that. I'll grab a new sheet of paper real quick. So in this case, we saw that the probability that it's greater than 5 was the 54 out of 64. So that must mean that the probability that it is not greater than 5 were the other 10 out of 64. So let's look at both scenarios. If we're going to say that the sum exceeds 5 exactly once, that means I could have the case where on my first toss it was greater than 5, and on my second toss it was not greater than 5. So that's one case. Or, so we always throw in your plus when you say the word or we could have the case where my first toss is not greater than 5, but my second toss is. So there are two ways that this could happen. So it could go in either order. So really, if we kind of multiply these guys together and multiply these guys together and just add those two numbers together, or you could say it's just 2 times this, because really I'm going to get the same result in both cases, since all I did was flip the order of those. So you're going to have 2 of these results, and so you could just multiply that result times 2. That would also get you the same answer. So moving on to number 8. Again, we got independent events. Given A, given not A or not B, and so now we're asked to find a few things. So again, we've seen already with a couple of Venn diagrams that I've shown, the area that is not A or not B is everything except A and B. So when you look at a Venn diagram for something like this, so remember what we said, if I were to shade everything that's not A, so that's everything that's not A, or everything that's not B. So now I got everything going this way for everything that's not B, so I'm just going to shade everything outside of circle B, or set B. So that's the look that we get. So you can see it is everything except A and B. So one way to look at this idea is anytime you have not A or not B, that is equal to 1 minus A and B, which you can see in the diagram that I have right here. So remember, the whole thing has to add up to 1 since we're dealing with probabilities. And so if I just take out the A and B part of it, I am left with the not A or not B. So I know all that red area is the 0.9, which must mean that this guy on the inside is 0.1, since the total has to add up to 1, 100% for probability. So anyway, now if we start looking at a few cases here, we do know that A times B must be 0.1, since these were independent events. So I know that to get A and B with independent events, I have to do A times B. And so in this case, I know A and B is 0.1 from what we've already figured out. They told me that the probability of A is 0.4. And so I can now solve that for the probability of B. So if I just divide that 0.4 over, I get 1/4 for the probability of B. So now if I wanted the probability of B given not A, let me just fill a few things into the diagram before I start laying out the setup for part B here, because that's a pretty tough setup unless you have some good numbers to look at. This is where a Venn diagram really helps out with cases like this. So again, we already know that all of set B is 0.25. If I take out what we already have in set B, that leaves me with 0.15 for the B only area. All of A we knew was 0.4. If I take out the 0.1 that's already in A, that means this guy has to be 0.3. And if I add those up and subtract it from 1, that tells me what's out here on the outside. So 0.55 if you add all that together, which means you got 0.45 on the outside. So now that we know what all the numbers are, it's a lot easier to figure out this setup right here. So the probability of B given not A, so B given not A. So remember what I said before, you always put the AND statement on top. and you always put the given on bottom. One thing that you can take advantage of in this problem, because they are independent events, there is a shortcut to your givens. In independent events, if you can see what's going to happen over here, remember in independence, you can multiply to get this, which means I'm allowed to cross those out only if the events are independent. So if I were to cross those out, what am I left with? I'm going to be left with just b, which we already know is 0.25. So that would be a great way of getting that answer. There's a few ways you could do this. That's the one way. That's probably the shortest way. So remember, in an independent case, the initial item is your answer, but only if the events are independent in a given scenario. You could have gone another way if you didn't recognize the shortcut. You could have said, well, these are independent events, so let's actually multiply. So if I did b times, so here's b, times not a, so not a, so if all of a is 0.4, not a must be 0.6. And again, I got not a on bottom. So even now you can see with the real numbers thrown in how I'm allowed to do this because the events were independent. You could have just looked at the Venn diagram and said, where's the area that is b and not a? And if we look at this, so all the things that are in b and not in a are this guy right here. So this is the one guy that is in b and is not in a. So you could have said, well, that's 0.15, and then you could have said, well, on bottom is not a, since a was 0.4, not a was 0.6, and I could divide and still get that same answer right there. So there's a few ways you could have done it, just whatever you see is the easiest route for you. Moving on to number 9. So one of two coins is known to be biased, so the probability of heads is 7/16. The other coin is fair, so 50-50. So the probability of a head is 1/2. So one of the coins is chosen at random and is tossed, showing heads. So what's the probability that the coin was biased? So one thing that really helps with these type of problems would be a tree diagram. So that's what I would do for number 9. So consider what is going on in this. What are the probabilities that we're considering? What are the events? So in this case, the first event that is being done is randomly choosing a coin. So that's the first event. So we have two coins, and so the first event is which coin we're going to choose. I can either choose the biased coin, or I can choose the fair coin. In either case, that's a 50-50 split as to which one I'm going to pick. So there's two coins to choose one, and we are going to randomly choose one, which means that's our first event in this probability case. In the second event, we would say, okay, now what are the outcomes? On the biased coin, they told us that heads is 7/16, which must mean that getting a tails is the remaining 9/16 in that scenario. In the fair coin, we knew it was 50-50, so could have been heads or tails, and those probabilities are 50-50. All right, so there's a good looking tree diagram, so now we can go on to answer the question. So what's the probability? Sorry, let me start right here. So one of the coins is chosen at random and is tossed, showing heads, which means we're going to get heads as the result. So it's like given information right there. So what's the probability that the coin that was tossed was the biased coin? So what's the probability that we got this one, knowing that heads was the outcome? So one thing you got to remember on this is because we were given some information, right? This is our given. We already know the result is heads. So that's like saying, what's the probability of A given B? So in this case, our given is that we got heads as the result. So we're saying, what's the probability that it was the biased coin given that the outcome was heads? And so that's really the information that we're being given on this. And so remember what we said before. Given goes on bottom. So the probability is that we got heads as a result. Let's look at those cases. That's going to be our denominator. So right here, if I were to say, well, what if it was the biased coin and landed on heads? So if I multiply those two together, I get 7 out of 32 for that case. if I look at the other case where I could get heads, so what's the probability that it was the fair coin and landed on heads? That's 1 out of 4 if I multiply those together. So those are the two cases that could show up heads. So that makes up our total sample space, or our total possible to choose from. So that's our given scenario, so that's our denominator. Now from those cases, what's the probability that it was the biased coin? And so this is where, remember what we said for given cases, you do the and scenario on top. So what's the probability that it was biased and heads out of heads? So we already got the heads cases on bottom. The and case goes on top, which means what's the probability that it was biased and heads? And that was this case right here. So that becomes our numerator in this setup. And so that's the way I would set that one up, and then just the rest would be calculator for that. So I already went ahead and punched that into my calculator, so here's what it looked like. So that was my setup for the numerator. Don't forget those, or sorry, for the fraction, don't forget the parentheses around your denominator if you're going to put all that in one shot. And so I just converted that to a fraction, and that's what we got. All right, moving on. A few more. We're jumping down to number 11. So now we got two standard 6-sided dice. Again, we're now looking at a sum, as the probability of x is going to be a sum. So what's the probability that the sum is 3? And so if you kind of looked at that lattice diagram that we've already talked about for a case where the sums are 3, only a couple of those could either be a 2 and a 1 or a 1 and a 2. So only 2 out of the 36 cases have a sum of 3. So that's for part A, which of course we would reduce to 1/18. What about the probability that the sums are greater than or equal to 8? So again, if we kind of look at a lattice diagram on that, cases that have a sum of 8 or more. So let me find our sum of 8 column, or diagonal. So it would start right here. So with a 6-2 or the 5-3, so it's the one that we've already kind of looked at earlier. So this one said a sum of 8 or more, and so we're kind of looking at all of those cases that have a sum of 8 or greater. And so if I were to add all those up and put it out of 36, so you're looking at 5 plus 4 plus 3 plus 2 plus 1. So if you add those up, put it out of 36, that would give us our answer. Number 12, so we got A and B are independent events. Again, super huge word right there is independent, which means I know that A and B is A times B. But that's only true if the word is independent is there. So what's the probability of B given A? Remember what I said earlier. If the events are independent, the shortcut on that is simply whatever comes first is your answer. So what's the probability of B? And so that's something we're going to solve for. So in this case, remember that A times B is the same, A and B is equal to A times B. So A times B, simply because they gave us the word independent. So now if I divide the 0.9 over, 0.5 over 0.9 is our probability of B, which would just be our answer for both cases, simply because the events are independent, which means in a given scenario, whatever comes first is your answer if the events are independent. So that would be my answer for both questions. So jumping down to 13, back to our two dice. One's blue, one's yellow. 1 through 6 are shown. So what's the probability that the number on the yellow die is odd? So in this case, now you're kind of looking back at that lattice diagram. So in this, identify one of these as yellow and one of these as blue. 5, 6, 1, 2, 3. So let's just say this is our yellow case and this is our blue case. So numbers are shown. So what's the probability that the yellow die is odd? So here's our yellow die, and so we're just going to look at all the odds on that one. So you would have 6 of those here, 6 of those here, and 6 of those here. and so that's simply half of the cases. So 18 out of 36, or 1/2, would be our solution for that one. So moving down to part B, what about the number on the blue die is less than the number on the yellow die? So if we just start looking at those cases, we'll just kind of work our way down the list. So for the blue die is less than the yellow die. So if the blue die was a 1, sorry, let me do this. If the blue die was a 1, that means the yellow could be 2 through 6. So all of those would be good. If the blue die were a 2, then the yellow could be 3 through 6. If the blue die were a 3, we'd have 4 through 6. Hopefully you notice the pattern here. And so those X's, I would just add those up and put it out of 36. That would be all of the cases that fit that scenario. Okay, last one. 14. So 200 people. Let me bump down here. So 200 students were asked if they prefer vacation in the mountains or the sea. To me, that's a no-brainer. I'd pick the ocean every time. But anyway, of the 94 boys in the survey, so keep in mind there are 94 boys, and that must mean the other 106 students were girls. So anyway, 49 of those boys said they would choose the mountains. 43 girls also said they would choose the mountains. So let's kind of complete the table. So we can use a table, or we can use a different method, is what that's saying. But let's just complete the table so we have it. So mountains, for total on those, if we add those up, looks like 92 for total mountains, which means if we kind of work our way through the table here, that means the other 108 students must have chosen the sea, since there was a total of 200. A little subtraction here, so there were 94 boys, 49 of them chose the mountains, which must mean the remaining boys chose the sea. So if we subtract, it looks like 45, I think I did that right in my head, would be the boys that chose the sea. As far as the girls go, if you kind of work your way over, for choosing the sea, of this 108 girls, of the 108 people that chose the sea, 45 already were chosen from the boys, which must mean the other group of this 108 were girls. So a little subtraction, 108 minus 45, looks like 63, I believe. I think those add up right. So again, total girls, we already knew there were 106. That was something we kind of identified right off the bat. So there's all the numbers, and now it's probably easier to now answer these questions. So student selected at random prefers vacation at the sea. So it looks like there was 108 out of 200 that chose the sea. And then the last part here, student prefers vacation at the sea, given that it's a girl. So remember what we said before, we're going to say probability that they're picking the sea, given that it's a girl. So the way I always set these up is I do the and statement on top, so sea and girl, given on bottom, so girls are on bottom. So in this case, we know that as far as girls, there's 106 out of 200, or you could just put the 106 if you want to do it that way. So probability that it's a girl, probability that it's the sea and a girl, that was those group right there. So those are the girls who chose the sea. So 63 out of the 200 fit that probability. So you can kind of delete the 200s at that point and just call it 63 out of 106. And that's our answer.